So in this lecture, we are going to discuss about the loss function interpretations. Okay, so loss function interpretations about our support vectors machines. How support vector machines equations are compared to geometrical point of view and loss functions point of view. In that is, here we are taking loss functions as Hinge loss. Okay. So if you just remember in a previous series of lectures, that is uh, logistic regressions, if you just remember, here we are taking the loss functions as logistic loss. Plus here there we are taking some regularizer. Okay, in linear regressions, if you remember, they are also same. Instead of logistic loss, there we are considering the linear loss, and also there we are consider some regularizer term. Similarly, for our support vector machines, here we are also consider one loss, that is this kind of loss function is called our Hinge loss function, and also they have some regularization. Both are the same, just our framework is the same, just we have changed the our loss functions. If simple changing loss functions, we are just change our model. This is the beauty of loss function interpretations. This is the for each classifier and regression technique, we will see that just simple the loss functions which we simply change our whole model. Okay, so before going to discussions, just to see the, I am taking a picture from Wikipedia. Just see this picture first. Just if you see this picture, so here if you just remember, this is this line, that is our sample. This line, if you just remember this line, this is simple what, this picture, this line is our 0 1 lost. We see that this line is our 0 1 loss. Okay, and simply this line, if you just see this line, that is yellow line, this line, this is our simply logistic loss. This is the simple logistic loss function. Because why? Because we are see that in logistic loss functions, we are seen in loss function originally happen in 0 1 loss, but actually in 0 point these functions is not differentiable. So this function 0 1 is modified by this one, this logistic loss, and using this loss we are interpreted our classifications simply. And if you see this one is called the square loss. We see this square loss in linear regressions, and a sample this one, that's this pink line, is called the Hinge loss. We see these functions in this lecture, how these Hinge loss are interpretable in support vector machines. Okay, let's go there. So first redraw this picture out. Just redraw this picture. First we are redraw this picture. It's okay. And now we extend this line this side. Okay, now this is one. Suppose this is our axis. Here we are taking yi. So I am taking the yi into f of xi. Okay, so we are see our f of xi changes only. Yi is fixed for every. Here what is our f of xi? Here simply our f of xi will be w transpose xi plus b. This function, and simple called this one is Zeta, and this point is our 0 point, let's take, and this is our 1 point, let's take. This is our positive directions, and this is our negative direction. And let's take this is our loss function. This independent axis is our loss axis. Loss axis. So if you just see, if this one is 1 in 0 1 loss, if you see, if you just see, if you just see our geometrical intuitions of the SVM as well as logistic regressions, then you can easily see that if simply if Zi, that is these multiplications, if these multiplications is greater than 0, this means what? If this means this xir means xi is correctly classified. This means that in everywhere, as well as in logistic regressions and also SVM, in linear regressions, everywhere we've seen that if zeta is greater than 0, then our data points is correctly classified. Simply, similarly, if zeta is less than 0, then our data point, that is xi, is incorrectly classified. Is simply incorrectly classified. Just draw this. In we see that in logistic regressions we got the 0 1 loss. So 0 1 loss will be like that. If it is greater than 0, then it is correctly classified. It is then xi is correctly classified. Zeta is greater than 0, then in 0 1 we got the value loss function 0. Just see the pinking, and it is less than 0, then incorrectly classified, and we got this one equals to 1. Simple. This one is our actually 0 1 loss. Now see this one. Here I am taking the blue one. Yeah. Just see this one. If zeta is now we are going to write the this formula, Hinge loss. Just see the Hinge loss. If it is zeta greater than 1, then it is our loss function is 0, that is correctly classified. If this one is just in here, okay. If zeta is less than 1, now we will discuss everything. Just first draw this, what is Hinge loss. Just we will see. We will see everything. Okay. If you just see this one, this is one. This is our 0 1 loss, and the blue line here, this line is our Hinge loss. Just see this picture first, then I will discuss everything step by step. Okay. This is our 0 1 loss. If you see in 0 1 loss, this function is not differentiable at the point 0. Just see this. Just see the here. In 0 1 loss, in 0 1 functions, 0 1 loss is not defined, so it is not continuous, as well as it is not continuous differentiable in the point of 0. So 0 1 loss function is not differentiable at 0. And again, if we consider the Hinge loss, just see at the point 1, it is not differentiable. At the point 1, it is not differentiable. So Hinge loss function is not differentiable at the point 1. Now how we interpreted these Hinge Loss functions to our SVM. Now we are going to discuss this thing. Okay, so let's go. So we see that what we'll see. Just I am just simple write the mathematical form of our Hinge Loss. First write down the mathematical form of our Hinge Loss. So our Hinge Loss functions will be like this. We see that if Z1, this is our Z1, if Z1 is greater than 0, then the Hinge loss is 0. If Z1 is less than 1, or if Z1 is greater than 1, this loss functions Hinge loss is 0. And if our Zi is less than 1, then we will take this value, that is 1 minus Zi. Means what? If we just taken simple this one, the here value, if we just take here 0.5, then this value is 0.5. This value is 0.5. If we are taking here, suppose here I am taking here minus 1. So what will be now the value? If I just taking, that is 1, just I am calling this function. This 1 is equals to 1 minus Zi. So what will be the value? If I taking minus 1, so what will be minus 1 into 1, that is 2. That is 2, where 2 value this one? That is 2. So okay, this function 1 minus Zi. So just write down this mathematical function, just write down. If our Zi greater than is equals to 1, then our Hinge loss is equals to 0. If our Zi less than 1, then our Hinge loss is equals to 1 minus Zi. Okay, I think this mathematical formulation clear from this picture. Okay. So now I am just write these 2-line equations in single line. How I write this? Just see this. How will I write this equation? If I write these 2-line equations in this form, max of 0, 1 minus Zi, then this thing are same as this thing. Why? So let's take case 1 first. Let's take case 1 first. Case 1. In case 1, let's take first our Zi is greater than is equals to 1. Let's take this side. So if this Zi greater than is equals to 1, then what is the value of 1 minus Zi? Then what is the value of 1 minus Zi? So this value will be now negative value. This value takes the negative. This is negative value. This means what? If this is negative, and here I am considering the maximum functions among 0 and 1 minus Zi, what will be the maximum? 0 is the maximum. So in this case, the maximum of 0, 1 minus Zi is equals to 0. Okay. Now let's take case 2. In case 2, let's our Zi is less than 1. This means what? If our Zi is less than 1, then 1 minus Zi is what? Is positive value, and it is positive value, and it is also greater than 0, or we can easily call, or we can call it is greater than 0. This implies that what? This implies that our maximum of 0, 1 minus Zi is what? Maximum. This is positive value and greater than 0. So maximum of this, what will be our maximum? This maximum will be 1 minus Zi. Just see this formula. If greater than is equals to 1, then Hinge loss is equal to 0, and if it's less than 1, then Hinge loss is equals to 1 minus. Both these equations, both are the same. Just here we are writing it is 2-line. Here I am using the simple max function. I am just represented this thing. Okay? Both are the same. Both are the same thing. Now, I think you will understand. I will understand these functions of the Hinge loss functions, about the Hinge loss functions. Now, let's compare this thing in geometrical point of view. Let's compare. So now, geometrical formulations and loss functions. Let's geometrically formulate this thing. And interpreted this thing with our loss function, that is here our Hinge loss minimum function, that is our Hinge loss. Just discuss of. So first, if you just first before this going to the discussion, first draw the picture, it will be better for you. So as previously I am taking the pi plus plane in blue color. Okay, this is our pi plus plane. And what is its equations? Its equations is simply, so I think everyone know what is the equation. So simply the equation is w transpose plus x plus b is equals to 1. I think it is not a need to write here again and again. Now I am just draw our negative plane, negative pi minus plane, that we call a negative support vector planes. It is pi minus, and its equations we already know, w transpose xi plus b is equals to -1. I'm not writing this thing again and again. Okay, this is our pi plane, this is our main hyperplane, this is pi, and these equations we consider w transpose xi plus b. Simple, just write down, instead of xi, just I'm writing x plus b. Okay. And what is our w? Simply w is not a unit vector, and it is simply perpendicular to our plane. It is not a unit vector. Just remember, it is not a unit vector. I am repeating again, this is not a unit vector. This is simply perpendicular to our h plane, because h plane is parallel to each other. So simply, let's take our directions of the w is the same direction of positive points. If you interested, you can take it is negative directions, and according to that you can calculate it. Here in general, every author, every books are taking it is at positive directions, so I am taking here it is in positive directions. If you are interested, as a homework you can do that, in take it as a negative directions and do your calculations accordingly. Okay, so first take the points which are classified properly. So if our positive data point are properly classified, then these points will be in these directions, in this region. This is simple, this is the positive region, this region. If you just remember, this is our positive regions and this is our negative region, this is our negative region. Just if our points are properly classified, then this point will be where? Here in this region, that is positive region. Okay, if this is in positive directions and it is correctly classified, then what will be the value of zeta now? And just if you remember our soft margin SPM class, just if you remember the lectures of the soft margin SBM, then you can find if our points are correctly classified, then there we got our zeta's value is equals to simply 0. Okay, so just write down this thing. If xi's are correctly classified, then these points, what will be the value? Then zeta i's value equals to 0. Okay, simply we have seen this thing in soft margin SPM. Just if you just forget this lecture, just go to this lecture and you can easily find from there. Now let's take a misclassified point. If I are taking, suppose a misclassified point is here, this point simply misclassified point. And if you just remember, if you just remember this thing, so the point, the value of this, the if you just simply find this point of this equations of this plane from this, suppose let I'm interesting this point. So what will be the distance of this plane? This point. What will be the distance of this point from this distance? This distance will be, if you just simply calculated here. If you just simply calculated here this for this point. So for this point, yi w transpose xi plus b. Suppose let's take it's a point. Suppose let's take it's a point xj point. And so here yj into w transpose xj plus b will be what? This value will be simply negative value, because directions of the w is equals to in positive directions, but this point is in opposite directions of our directions of w, and as well it is a misclassified point. Simply this value is negative, this value is negative, this thing. Suppose let's take this thing is equals to our, suppose let's take this distance is here, from here to here this distance is this one, and let's take this distance from here to here, this distance, from here to here this distance is what? From here to here, if we just consider this one. So let's take another color. Just I'm using the green ink. From here to here this distance is 1. Now if we interest to find the distance from the correct hyperplane, so here correct hyperplane is what? This is a positive point, and here correct hyperplane is pi plus. So if we are count the distance from the correct hyperplane, let's call this distance for the point xj is dj. So like just write down this thing. So we are interested to find the distance dj. So dj will be what? Dj will be 1 minus, we already seen, yi, this distance, this one distance, yi w transpose xj plus b, sorry, it will be yj plus xj plus b. From here to here this distance will be total 1 distance, plus because it is the same one and it is the opposite directions, it will be minus. So this total distance will be 1 minus this one, and we call this thing as z. So this thing, if you just adjust this thing in science, then you will always get this total distance will be positive, because 1 minus this one, and this thing is total, this thing is also negative, so negative minus negative, it is also positive. So total dj now then will be positive. So actually distance is positive, always positive, it is not a negative distance. So from this sign, from if you just taking the sign interpretations, then it actually this value is what? Just I am writing this value is negative value, and 1 minus this thing, this will adjust automatically. So minus into minus is equals to plus. So because of understanding purpose, I am just simply writing this thing. So for dj point, this value will be 1 minus zj. Okay, this value is simple 1 minus zj. And just simply, if you remember the soft margin SVM, we are calling this thing as zeta z. From our correct hyperplane to our misclassified point, this thing we are calling the zeta z functions. From here to here, this thing is called the zeta z. So just simply, if you write down zeta z, it equals to distance for xj to the plane, to the correct hyperplane, to the plane pi plus, that is our actual correct hyperplane for our positive point. For this is a pi plus is the actually correct hyperplane for our positive point, and pi minus is the correct hyperplane for our negative points. So zeta is simply the distance from the zj to the our plane pi plus, to our plane pi plus, that is equals to, that we call z dj, and simply this one is equals to 1 minus zj. Okay, it's simply this one is equals to, just I think just you have already, we have discussed this thing in soft merging SVM, just I am repeating this thing again and again. So zeta j will be finally 1 minus zj. Okay, when, and these situations when occur, if our zeta xi correctly classified, then this zeta value is 0, and it is misclassified. If our data point is misclassified, then zeta j's value is greater than 0, when xj is misclassified. Okay, I think these two things we are already discussed in soft margin. I am just repeating. Now just I am comparing these two concepts with this function, that is our Hinge loss function. Just compare this. So what we get in our Hinge loss? Just remember our Hinge loss function. In Hinge loss functions, we get our Hinge loss functions is max of 0 of 1 minus zi. This is actually our Hinge loss functions, and this, if we call it zeta I, then just simply we got this function zeta I. So zeta I is 0 or this one, and zeta I to when it is 0, simply this one is correctly classified, and when this one is correctly classified, if yi into zi, yi into y, simple zi means what? Zi means just see this thing, zi means this one, just see this thing. Just I'm just writing this. Our zeta means what? Zeta means yi w transpose xi plus b. This is actually zeta I, and zeta is greater than 0 when our when our points are correctly classified. Then if our correct, that's only it is greater than is equals to 1. Then only it is correct if greater than is equals to 1. Okay. Okay, greater than is equals to 1, then only this possible. Okay, and means greater than is equals to 1 means in these directions as well as in these directions. So in this case, what we will get, if zeta greater than is equals to 1, then we get then we get our is equals to 0 if simply zeta I, that is yi w transpose xi plus b less than 1, then we got that zeta I greater than 0. Okay, and this is the same concept, just see this thing, this is the same concept to our Hinge loss. Just compare this thing with our Hinge loss, then these both the things are same, both the same things are same. Okay, I think the soft margin concept, soft margin SVM concept and Hinge loss functions both are the same concept, just the two different interpretations, that's from two different angle. If you see, the main thing is the same, both the thing is same, just we have seen this thing into different side. Okay, now just write down the soft margin SVM equation, just write. Now we are writing the soft margin SVM. what we will doing in optimization, we are interested to do the minimizations of our norm w by 2 plus sum. Just I am omitting the average term. I am simply taking here the average total sum of our sigma is both are the same concept. Since 1 by n is constant, we can easily neglect it. It is not a main matter. Don't be confused why I am neglecting this 1 by n, that is average term. If you are interested, then you can easily take, but for simplicity of our math, I am neglecting 1 by n for average distance. Just simply I am taking the sum distance of ours. This zeta is sum distance, right? And we have as well, we have some constants. So what is our constant? This constant is simply yi w transpose xi plus b. Okay, this is our constant, and this was too simple. Just I am simply modifying this thing. Just if you simply just I am writing 1 minus zeta is this will I am taking in is soft margin SVM chapters. Just I am just converting the 1 in the left side from right to left. I'm just or nothing else. Simple this one. And as well our zeta is greater than 0. So these equations we have seen in our soft margin is just remember thing. If you just forget, just revisit this chapter, then you can easily find it. And this thing, both the things we have discussed in soft margin is okay. Now the main thing is that now we are going to compare this soft margin SVM with our loss minimization stuff. Loss minimization. So just and again written the loss minimization equation. So loss, if you just write the loss minimization equations, so our loss minimization equations is simply we are interested to minimize the loss functions. What we'll get in our loss function, this one, these are loss minimization function. Just we are want to minimize this one, that is I is equals to 1 to n max of hinge loss, that is 0 minus 1 minus this one zeta I mean this one 1 minus, simple instead of z I am writing here yi into, just I am using this curly bracket, w transpose xi plus b. Here simply this one is our zi, both are the same thing. Plus we have some hyperparameter, that is lambda plus norm of w. Suppose here we are taking the L2 norm. Okay, no, don't be confused. Here I am taking the L2 norm. But just see, these both the same equations are the same. Thus we are visualize this thing into two different angles, but both the equations. How this is same? Just see it. Just see it. First we are considering this theta, this w term and this term. Just I am taking here. Just I am taking the euro. Just see this thing. Just I am first comparing these two things. Both are actually the same term. Actually, end of the day, we are interested to minimizing this total thing. Okay, both are the same thing. Both are the normal of w. See here actually 1 by 2 is the constant. You can easily neglect this thing. Just see this portion and these portions. Both are the same thing. Just we are taking the norm of the w. So in this case, actually this is our what? This is our regularizer term. So and simply here it is also a, actually we have taken it is a regularizer. And the end of the soft margin just if you revisit the soft margin SPM lectures, then in the end of this lecture I am calling this as a regularizer because of simply this comparison. I am simple this is the same thing. Now the question is that, so just write down it, norm of w greater than equals to 0, norm of w equal greater than equals to 0. This is the weight vector, we are interested to find it, and minimum of W is same as mean of square. Okay, both the things are same. Now just let's consider these two things. Means this thing and this thing. Okay, this is actually what? This thing actually, this one actually loss. This is actually loss in the soft margin XPM. We are trying to minimize this loss value. Okay, if simple, why loss? If zeta is equals to 0, you can see if zeta is equals to 0, then it is correctly classified. Correctly classified. If zeta I greater than 0, only then it is incorrectly classified. So simple, this you can take it as a loss function. So we want to minimize this incorrectly classified point. We want to minimize our misclassification point. Simply, if we want to minimize our misclassified point, simply this we want to minimize this sum of the loss. So for this, it is a simple loss function. And here, just we are comparing this thing. This is a what? This is our simple hinge loss. This is our hinge loss function. Okay, both the things are same. Here also we are interested to find the W and B as well. This is a hinge loss. Both the things are same. Both the thing. Here instead of just see this function zeta. Just see this. Just see from the same thing, from the same thing. Just here zeta is equals to this one. Here simple zeta is equals to this one. And we have taken the C. Here you have taken the summations here. Here also taking the sum. The main thing is that here C parameter. The main thing is that here parameter. This parameter here in soft base may we have taken the parameter C, and in the loss minimization we have taken our parameter lambda. But these are actually hyperparameter. But this will work in a different perspective. If we just taking the C parameter in soft if you see the soft margin SBM, then how the C will work? If we increase the value of C, then what? Simply, if we increase the value of C, then we give the priority of this one. This if we give the priority of minimizing of this one, this means we are going to overfeed our model. Means this we are going to minimize our error. We are giving the priority to minimizing this error. This loss value we are giving the priority to minimize our loss value. So our model going to overfeed. Okay, if C we decrease the value of C, so we give the less important, so we are avoiding our misclassified point. So in such cases our model will goes to underfit. Okay, so in soft based medium just we see the relations, we have seen these relations. Now coming to our loss minimization perspective, if you just see our loss minimization perspective, if we simply increase the value of lambda, then we are giving the more priority to our weight vector, that is regularizer term. If we give the more priority to our regularizer term, simple we have seen in logistic regressions that our model going to underfit. If we have decreased the value of lambda, simple our model is going to overfit. So both these things will the same work, but in different perspectives. Okay, I think this concept just I'm just again remembering. If you remember the scalar library, if you just simply, if in Python, if you just see the scalar library, then our hyperparameter, we have used our hyperparameter for logistic loss. for logistic regressions and also SVM. For both the cases, we have taken the hyperparameter C. Okay, because C is simple nothing, it is 1 by lambda. Both are the same thing. Only we have taken C here. Our in logistic regressions, we increment the value of C, then then it will overfit, and if decrement the value of C, then it will underfit, as well as it is SVM. But we have in mathematically we have taken the value of C regularizer in logistic regression lambda, and in SVM we have taken the hyperparameter C. But both are the same. Both are the both are the same, both are the actually a hyperparameter, and one is inverse to another's. Okay, but both the things are will the same, do the same work. I think now this thing is clear, all of you. What is the why we are in scale and why we are taking the hyperparameter C, and how it is the related to our SVM model, and how the soft geometrical view, the geometric, and we see the geometrical view, and as well as is and its loss functions point of view, and both are the same thing at the end of the day. So just we are seeing this thing in two different angle. Okay, I think thus this concept is clear, all of you. If you have faced any problem, please I request you, please revisit this lecture again. Then I think after this, if you had any confusions, please comment below, and I am always hungry to help you. Okay, thank you.